So this is lecture 2. Yesterday, we studied divisibility and greatest common divisors. And one of the most important results from yesterday is the following. Actually, there were two. The first was the Euclidean algorithm to very effectively compute the GCD, greatest common divisor, of two integers. And second, the fact that if D is the greatest common divisor of two numbers A and B, so this is the notation for greatest common divisor, then there exists, so in mathematics, a backwards capital E, there exists.
Chandrea, can you mute your phone? Okay.
Just 1 second. So then there exists, that's what this symbol means, there exists integers u and v such that you can write D as this linear combination AU plus BV. The numbers U and V are not unique, but they always exist. So for example, if we take, let's say, A equal 5 and B equal to 13, then the GCD of 5 and 13 is equal to 1. And we can solve the equation 5u plus 13v equals 1. For example, 5 times 8 and 13 times minus 3 is equal to 1. So you could take u equal to 8 and v equal to minus 3. So this is an extremely important fact, theoretically and practically, in cryptography. Okay. Any questions about what we did yesterday? Then today, we're going to go on to the next section. So this was in section 1.2. And now we're going to start section 1.3, which is modular arithmetic. And people always like to compare this to telling time. You know, you have a clock, and if you are at 5 o'clock, and you go 8 hours, let's say 9 hours later, you're not at 14 o'clock, 5 o'clock, and then you go 9 hours later is 2 o'clock. 5 plus 19 equals 2 when you're telling time, right? And if you understood that in elementary school, then you will understand modular arithmetic in college. Namely, we say, so we fix an integer m, positive integer, generally, in fact, m greater than or equal to 2, so it's a positive integer, which is called the modulus. And we say that this is how we write it in words. A is congruent to B modulo M. And the notation for this, A, 3 lines, B, mod M, if M divides the difference, A minus B. All right? So that's all there is to it. If M divides A minus B, we say A is congruent to B mod M, and we write it like this. Okay. So for example, 5 is congruent to -7 mod 12, because 12 divides the difference, 5 minus -7, which is actually equal to 12. Or 31 is congruent to, I don't know, 15 mod 8, because 31 minus 15 is 16, which is 8 times 2. So 8 divides 31 minus 15, right? Any questions about this? This is the fundamental definition in modular arithmetic. So, for example, A is congruent to 0 mod M means M divides A minus 0, which is A. So A is congruent to 0 mod M is just another way of saying that M divides A. And one of the nice things about congruence is that there's a very nice arithmetic for congruences. And many of the properties are collected in this proposition 1.13 in the text. So we have an integer M greater than or equal to 1. And first proposition says that if A1 is congruent to A2 mod M, and B1 is congruent to B2 mod M, then we can add the congruences. A1 plus B1 is congruent to A2 plus B2 mod M. And we can subtract the congruences. And we can multiply the congruences. Can't divide. So then there's a second part to this proposition, but let me prove this first. Proof. A1 congruent to A2 mod M means what? A1 minus A2 is divisible by M. Say this is equal to M times Q for some integer Q. And B1 congruent to B2 mod M means B1 minus B2 is divisible by M. So maybe it's M times R for some R. Right? So A1 is A2 plus MQ. B1 is B2 plus MR. If I add, so these are equations, not congruences. If I add, I get A1 plus B1 equals A2 plus MQ plus B2 plus MR. That's A2 plus B2. And then these two terms, I can factor out the M times Q plus R. So A1 plus B1 minus A2 plus B2 is a multiple of M, which means A1 plus A2 is congruent to B1 plus B2 mod M. And if I subtract, I would get A1 plus B1, sorry. Here I add, I get this. A1 plus B1 equals A2 plus MQ plus B2 plus MR is equal to this. And if I were to subtract these equations, I would get A1 minus B1 is A2 minus B2 plus MQ minus R. So again, A1 minus B1 would be congruent modulo M to A2 plus B2. So that shows you that we can add and subtract congruences. For multiplication, again, we have A1 is A2 plus MQ. B1 is B2 plus MR. If I multiply A1 times B1, that's A2 plus MQ times B2 plus MR. If I multiply, if I just expand all this, this is A2 B2 plus A2 MR plus MQ B2 plus MQ MR. This is just A2 B2 plus, factor out an M, A2R plus QB2 plus QMR. So this minus this is some multiple of R. It's a multiple of M. So A1, B1 is congruent to A2, B2 mod M. So that's all it is. You have, for example, 18 is congruent to 9 mod 3. 7 is congruent to 2 mod 3. If we add, we get 25 is congruent to 7 mod 3. If we subtract, we get 11 is congruent to 11 mod 3. We multiply, 7 times 18 is 126. It's congruent to minus 18 mod 3. Right, so you can check all of these directly, but they follow from these properties of congruences. Any questions about this? And then the second part of the proposition says the following. So you fix an integer A, and we have a modulus M. So there exists an integer B such that AB is congruent to 1 mod M, if and only if the greatest common divisor of A and M is equal to 1. So why is that? So here's a proof of this second part. Suppose the greatest common divisor of A and M is equal to 1. Then there exist integers U and V such that AU plus MV equals 1. But this says exactly that AU minus 1 is MV. So AU is congruent to 1 mod M, and let B equal this number U. So from this result about greatest common divisors of integers being represented by these linear equations, which came directly out of the Euclidean algorithm, we get this result. Okay. What about the converse? So suppose AB is congruent to 1 mod m. So then AB minus 1 is some multiple of m. So I say m times b. So AB minus mb equals 1. If D divides A and D divides M, then D divides 1. Right? If A is a multiple of D and M is a multiple of D, so is this number, which is 1. Which means the only positive common divisor of A and M is equal to 1. So this very important congruence, AB congruent to 1 mod M, is possible if and only if A and M are relatively prime. Moreover, there's a kind of uniqueness involved. So we're looking at this congruence, AB congruent to 1 mod M. It's sort of like saying that B is 1 over A. B is the inverse of A. Modulo M. And we know that if B1 is congruent to B2 mod M, then AB1 is congruent to AB2 mod M, because you can multiply congruences. What are the congruences we're multiplying? B1 congruent to B2 mod M, and every number A is congruent to itself mod M. Because A minus A is 0, and 0 is divisible by every integer. In particular, 0 is divisible by M. But the converse of this statement is true. If B1 and B2 are integers such that AB1 is congruent to AB2, they're both congruent to 1 mod M, then in fact, that only can happen is if B1 and B2 are congruent mod M. And there's a very slick proof of this fact. Proof. I'm going to look at a long congruence mod M. B1 is certainly congruent to B1 times 1 mod M. But 1 is the same as AB2 mod M. Because AB2 is 1 mod M, which is the same as B1A times B2 mod M. And AB1 and B1A are the same integers. So this is just 1 times B2 or B2. So this is that B1 is congruent to B2 mod M. So that is the proof of that remark. So let's look at just one or two examples. So 2 and 5 have greatest common divisor 1. So that means that you can solve the congruence 2b congruent to 1 mod 5. In fact, you can take b equal to 3. 2 times 3 is 6, and 6 is definitely congruent to 1 mod 5, but 6 take away 1 is 5. The GCD of 4 and 15 is 1. So 4 has an inverse. In fact, it's equal to itself. The inverse is itself. 4 times 4 is 16. Take away 1 is 15. So 4 times 4 is congruent to 1 mod 5. The GCD of 7 times 11 is 1. So 7 times B congruent to 1 mod 11 has a solution. Let's see, what's the solution? Well, you can just start running through numbers until you find one. And in fact, you will see that 7 times 8, which is 56, is congruent to 1 mod 11. We can think of this as like 8 is like 1 over 7 mod 11, because 8 times 7 is 1. That's sort of a curious way to look at this. Now, suppose we fix the modulus m at least 1. Suppose you take an integer a and divide it by m. So a is mq plus r. This is just by the division algorithm, or long division. And r is between 0 and m minus 1. So this says in particular, a is congruent to r mod m. So every integer, positive, negative, 0, every integer a is congruent to r mod m for some unique r in the set of integers between 0 and n minus 1. It has to be unique because if r and s are two numbers between 0 and m minus 1, and r is congruent to s mod m, then m divides r minus s. But if you think of it, here's 0 up to m minus 1. If you have two numbers, r and s, in this interval, the distance from r to s is at most, how far apart can they be? At most, m minus 1. If this number is positive and less than m, it's not divisible by m. So the only way m can divide r minus s is if r minus s is 0 or r equals s. So the numbers between 0 and m minus 1 are not equivalent or congruent to each other mod m. They're distinct. So we define this set z mod mz. And we're just going to use the same integers, 0, 1, 2, 3, the integers up to m minus 1. And we call this the ring of integers modulo m. So every integer is congruent to one of these and to a unique one of these. And we can define addition and multiplication of these numbers modulo m. If you have a and b, a plus b is certainly congruent to something in this set. And so a plus b is congruent to c mod m for some unique c in this set. And we define addition in this set modulo m, a plus b equals c in z mod mz. Some people put something like, let's say, a bar over these numbers to distinguish the number from the element of this set of, we can think of it as congruence classes. But our text doesn't do that, so I'm not going to do that. So we can work out, but let's take m equal to 5. So we have z mod 5z, which consists of the 5 elements 0, 1, 2, 3, and 4. And we can work out an addition table. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. And this is for plus. We just add them. 0 plus 0, 0 plus 1, 2, 3, 4. 1 plus 0, 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4. 1 plus 4 is the integer 5, which is congruent to 0. So in this set, in this ring, 1 plus 4 is 0. 2 plus 0, 2 plus 1, 2 plus 2. 2 plus 3 is 5, which is congruent to 0 mod 5. 2 plus 4 is 6, which is congruent to 1. 3 plus 0 is 3. 3 plus 1 is 4. 3 plus 2 is 5 is 0. 3 plus 3 is 6 is 1. 3 plus 4 is 7, which is 2 mod 5. 4 plus 0 is 4. 4 plus 1 is 5, which is congruent to 0. 4 plus 2 is 6, congruent to 1. 4 plus 3 is 7, congruent to 2. And 4 plus 4 is 8, congruent to 3. So that's the addition table in Z mod 5Z. What is the multiplication table? Well, 0 times anything is 0. That's easy. And multiply anything by 1 doesn't change it. 1 times 1, 1, 2, 1, 3, 1 times 4. 2 times 1, 3 times 1, 4 times 1. 2 times 2 is 4. 2 times 3 is 6, which is congruent to 1 mod 5. 2 times 4 is 8, which is congruent to 3 mod 5. 3 times 2 is 6, congruent to 1 mod 5. 3 times 3 is 9, congruent to 4 mod 5. 3 times 4 is 12, congruent to 2 mod 5. 4 times 2 is 8, congruent to 3 mod 5. 4 threes are 12, congruent to 2 mod 5. And 4 fours are 16, congruent to 1 mod 5. So this is the addition table, and this is the multiplication table. Now, okay, any questions so far? This is, if you haven't seen this before, it's a lot to absorb, and it takes a lot of time to work examples and get a feeling for what's going on. Yeah. Recall we proved that given an integer a, there exists a b such that ab is congruent to 1 mod m if and only if the greatest common divisor of a and m is 1. So let's say in Z mod MZ, A is what is called a unit if it has an inverse. If there exists B such that A times B equals 1. Equals 1 in Z mod MZ means congruent to 1 mod M. So, and we let Z mod MZ star, this is called the group of units in Z mod MZ. So for example, here, when M is equal to 5, what is the group of units in mod 5? Well, 1 times 1 is 1, so 1 is a unit. 2 times 3 is 1, so 2 is a unit. 3 times 2 is 1, so 3 is a unit. 4 times 4 is 1, so 4 is a unit. So this is all the non-zero elements of Z mod 5Z. Those are the units in Z mod 5Z. What about Z mod 24Z? What is the group of units? Well, it's the set of all A that are relatively prime to 24. So what are the numbers between 0 and 23 that are relatively prime to 24? 1, 5, 7, 11, 13, 17, 19, 23. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them. And it's important to know, given M, how many units are there modulo M. So for 5, the number was 4. For 24, the number is 1, 2, 3, 4, 5, 6, 7, 8. So in general, we call this number, or we denote this number by the letter phi of M. So phi of 5 is equal to 4, phi of 24 is equal to 8. So for every positive integer M, phi of M is the number of units modulo M, and this function has a name. It's called the Euler. It's spelled like this, but it's pronounced O-I-L-E-R. Euler phi, this is the Greek letter phi function. Very important function in algebra and number theory and many other fields. Okay. Now, in cryptography, we often think of it like this. You have someone, say Alice, who wants to send a message to Bob. So you have some matches and you want to encrypt and send the message to Bob, who will decipher or decrypt the message. And in many cases, so in many crypto systems, the first two that we're going to see are the two historically most important, something called RSA and something else called Diffie-Hellman, after two guys named Diffie and Hellman. You need to compute large powers of a number reduce mod m. So we want to compute some number g raised to some power a and reduced mod n. Okay. So what does g to the power a mean? You have g squared, g. I mean, you can just start multiplying g by itself. G to the fourth, g to the fifth, and eventually you get g to the power a. And then you reduce them all mod n. But doing this part, at least, requires a multiplications. Actually, a minus 1 multiplications. Like, suppose you wanted to know what is 2 to the 7th mod 5. So you compute 2, well, 2 is given. 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 120, 2 to the 7th is 128. So at each step, I multiplied by 2. So here was one multiplication to get from 2 to 4, another to get from 4 to 8. So there are 1, 2, 3, 4, 6 multiplications to calculate 2 to the 7th. Well, 6 isn't bad, but suppose we had to calculate 2 to the power, what is this number? 97,831,028,174. And I want to calculate that, I don't know, modulo 29. I could just multiply 2 by itself 97 billion times. Not a lot of fun, even for your computer. And then suppose we had a much bigger power. Suppose, in fact, it wasn't 2 to this power, but 2 to this power. That is some humongous number. I mean, that is so big it can't be done. So we would like to find a fast, efficient algorithm to compute powers g to the a and reduce mod n. So suppose we have the following problem. Compute 3 to the power 218 modulo 1,000. Again, you could compute 3 to the 218 by multiplying 3 by itself 217 times, and then reduce mod 1,000. That's 218 multiplications, roughly. Let's see if we can find a more efficient way. So we can do this with 217 multiplications. Suppose we want to do it with less. So take 218 and write it as a sum of powers of 2. So the way I would do this is what's the biggest power of 2 you can take? This is 128 plus 90. 90 is 64 plus 26. 26, let's see, what's the biggest power into 26? 16. plus 10. So this is 128 plus 64 plus 16, and 10 is 8 plus 2. So I can write in binary as a sum of powers of 2. 218 is 2 plus 8 plus 16 plus 64 plus 128. Or in terms of powers of 2, this is 2 to the first power plus 2 cubed plus 2 to the fourth plus 2 to the sixth plus 2 to the seventh. That is 218. Now, I want to compute 3 to the power 218 mod 1,000 with fewer than 217 multiplications. So 3, of course, is 3. 3 squared, that's 9. I know what 3 squared is. Suppose I take 3 squared and I square it. So to get from 3 to 3 squared, that's 3 times 3, and that's 1 multiplication. To get from 3 squared to 3 squared, I'm just multiplying this number by itself. This is 3 to the fourth. I get that with 1 multiplication. If I square this, I get 3 to the fourth squared, which is 3 to the eighth. That's 1 multiplication. I keep squaring. 3 to the eighth squared is 3 to the 64th. 3 to the 64 squared is 3 to the 128th. So I have 3 squared, 3 times 2 squared, 3 times 2 cubed, 3 times, oh, this should be 16. 3 to the 8 squared is 3 to the 16. And this is 3 to the 16 squared, 3 to the 32. And then I square that, I get 3 to the 64. So this is 3 to the 2 to the fourth, 3 times 2 to the fifth, 3 times 2 to the sixth. I get all of these numbers with how many multiplications? 1, 2, 3, 4, 5, 6. So I only need 6 multiplications to get these numbers. And then I'm interested in 3 to the 218. But that's 3 to the 2 to the first power plus 2 cubed plus 2 to the fourth plus 2 to the sixth plus 2 to the seventh. That's 3 squared times 3 to the 2 cubed times 3 to the 2 to the fourth times 3 times 2 to the sixth. That's 3 times 2 to the seventh. How many multiplications here? 1, 2, 3, 4. So altogether, it takes 6 plus 4, 10 multiplications to compute 3 to the 218. And mod 1,000, I just cross off all but the first 3 digits or all but the last 3 digits of the number. So 10 multiplications compared to 217. I did this with 10. Brute force would have been 217. 10 is a lot smaller. So this is a very clever and an extremely efficient way to compute powers. The text calls this the fast powering algorithm. It actually does this calculation. Let me actually do it because it's kind of fun. So let me make the same table you'll find in the book. So here is I, and here I want to put 3 to the I mod 1,000. So when I is 3 to the 2 to the I. So when I is 0, 2 to the 0 is 1. This is 3 to the first power, or 3. When I is 1, this is 3 squared, or 9. When I is 2, this is 3 to the 2 squared, 3 to the 4th. What is 3 to the 4th? 3, 9, 27, 81. What is 3 times 2 cubed? 3, when I is equal to 3, that's 3 times 2 cubed. That's 3 to the 2 squared squared. That's 81 squared. I guess you have to multiply that out. I mean, you have to do this with the multiplications. 1, 6, 5, 6. But mod 1,000, 6561 is congruent to 561. Mod 1,000. What's the difference? Is 6,000. This is 561. And I guess you can work out the rest of the table. The text does it. You get the numbers 721, 811, 281, 961. So 3 to the 218 is the product of 3 to what powers 2 to the I? It was 2 to the first, 2 cubed, 2 to the 4th, 6th, and 7th. So 3 218 is congruent to 9 times 561, 721, 281, 961. You do these multiplications, and the answer turns out to be 489 mod 1,000. Right. But you can see these calculations if you look at the text on page 25. So this general process is called the fast powering algorithm. And we're interested in computing efficiently g to the power a mod m. And what you do is take the binary expansion of a. So a is a sum of powers of 2, a0 plus a1 times 2 plus a2 times 2 squared, a3 times 3 cubed, and so forth, up to a sub r 2 to the r, where the ai's are 0 or 1, right? So if a power of 2 appears in the binary expansion of a, then the coefficient is 1. If it doesn't appear, the coefficient is 0. And so by successive squaring, you get g squared, g squared, which is g to the 2 squared, g to the 2 squared, which is g to the 2 cubed, and so forth. So you get g to the 2 to the r. So with r minus 1 multiplications, you get all of these powers of g. And if you want, you can reduce them at each step mod n. Suppose we let a0 be congruent to g, mod n, n. A1 is going to be A0 squared, which is congruent to G squared, mod n. A2 will be A1 squared, which is congruent to G to the 2 squared, mod n, and so forth. So as you compute these numbers at each step, you can also reduce the mod n just to make them smaller. And you put it all together and you're done. Any questions about this? This is it's sort of arithmetic from the point of view of computing, which is what is involved in cryptography. Okay, so we've just been talking about modular arithmetic. Now I want to go to section 1.4 and say a little bit about prime numbers. So an integer p is a prime number if p is bigger than 1, that means at least 2, and the only positive divisors of p are 1 and p. So what are the first primes? 2, 3. After 2, they're all odd, of course, because every even number is divisible by 2. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. There are a lot of them. And in fact, Euclid, 2,400 years ago, proved that there are infinitely many primes. So the sequence of primes goes on forever and forever and forever. One very important property of primes is something often called Euclid's lemma, that P be a prime number, that A and B be integers. If P divides the product AB, then P divides A or P divides B or both, of course. So if P divides a product of two numbers, it must divide at least one of them. And we can extend this as follows. If P divides a product of n numbers, then P must divide at least one of them. P divides AI for some I. So the proof goes as follows. Suppose we let G be the greatest common divisor of 1 and P. Sorry, G is the greatest common divisor of A and P. Now, this is a positive divisor of P, so this is either 1 or P. Of course, there's no other positive numbers that divide P except itself and 1. So if G equals P, then P divides A, and we're done. Because we want to show that if P divides AB, it divides A or B, and P divides A, then P divides B. But if not, if G equals 1, that means the GCD of A and P is 1, and there exist integers, U and V, such that AU plus PV equals 1. Take this equation and multiply by B. You get ABU plus PVB equals B. But we're told that P divides AB. So AB is PD for some D. So I can plug that in for AB. I get PD plus PVB equals B. Factor out of P, this is P times D plus VP equals B. So this shows P is divisible by P. P times this integer is B. So P divides B. So if P doesn't divide A, then it divides B. Now, again, it takes, if you know what you're doing, or if you've studied this and thought about this a lot, it takes only a couple of seconds to write this all down. But there really is a lot of thought involved in this, a lot of time required to understand it. And I sort of urge you to spend as much time as possible. This is really all one needs to prove what is called the fundamental theorem of arithmetic. It says the following, that A be greater than or equal to 2, then A is a product of prime numbers. So you can write A as P1, and you can have each of a prime occurring more than once. So P1 to some exponent E1, P2 to the E3, E2, P3 to the E3, and so forth, up to PR to the E sub R. Every number is a product of primes. And uniquely up to order. So if you take a number like, I don't know, 8,008, that's 8 times 1,001. 8 is 2 cubed. 1,001, I think, is divisible by 7, 11. Yeah, I think it's 7, 11, 13. So this is a product of powers of primes. I'm going to put off for a moment proving this, but these exponents are, so you write an integer as a product of prime powers. It's actually extremely difficult to do. So this is hard computationally. And this exponent we call the order. So, so if we have A is P1 to the E1, P2 to the E2, E sub R to the E sub R, where P1, P2 up to P sub R are distinct prime numbers, then E1 is called the order of P at E. So that's ORD is order of A at P1 and so forth. So let me just give an example here. I have 8,008 is 2 cubed 7 times 11 times 13. So the order of 8,008 at the prime 2 is 3, because 2 cubed is the highest power of 2 that divides 8,008. Whereas the order of 8,008 at the prime 7 is 1, because 7 to the first power is the power of 7 that divides this. If I take a prime, I could also, if I wanted, like this is 29 to the 0th power, that's just 1, that doesn't occur. So we could say that the order of 8,008 to the power 29 is 0. That simply is another more complicated way of saying that the prime 29 does not divide 8,008. I'm going to prove the fundamental theorem of arithmetic in a moment, but I just wanted to add one more point about units in Z mod P. Suppose we have a prime P and the ring Z mod PZ, which is 0, 1, 2, up to P minus 1. Then if A is an element of this ring and not 0, then the GCD of A and P is 1. Because if P divided A and A is not 0, then A would have to be at least P in size, but P is not in here. So every non-zero element of Z mod PZ is a unit. In other words, if I take the ring Z mod PZ, the group of units is all the non-zero numbers between 1 and P minus 1. And in fact, we have this, you can say the Z mod PZ is a field. And a field in mathematics is a set where you have addition and multiplication, and every non-zero element is a unit. That's really what that means. So we're going to talk about fields later in the course. The real numbers, the rational numbers, the complex numbers are fields, but they're infinite fields. Because there are infinitely many real numbers, rational numbers, complex numbers. The integers mod P, Z mod PZ, is a finite field. So it's very important that there are finite sets which are fields. First, the simplest is Z mod 2Z, which just consists of 0 and 1. And the only non-zero number is 1, and 1 is a unit, because 1 times 1 is 1. For addition, 0, 1, 0, 1, when you add, you get 0 plus 0 is 0, 1 plus 1 is 0, 0 plus 1 and 1 plus 0 is 1. And when you multiply, 0 times anything is 0, and 1 times 1 is 1. So the world's simplest field is this two-element field just consisting of 0 and 1. And if you're in computer science, you've probably used this a lot already. So how do you prove the fundamental theorem of arithmetic? We want to prove every number is a product of primes and in a unique way. So suppose we let A be greater than or equal to 2. Like, what are the numbers? Well, I have 2 is 2, it's a prime. 3 is 3, which is a prime. 4 is 2 times 2, it's a product of primes. 5 is 5. 6 is 2 times 3. 7 is 7. 8 is 2 times 2 times 2. 9 is 3 times 3. 10 is 2 times 5. 11 is 11, that's a prime. 12 is 2 squared times 3. 2 times 2 times 3. 13 is 13. So these first small positive integers are products of primes. I claim every number is a product of primes. So we're going to prove by induction that every integer A, at least 2, is a product of primes. We know it's true for A up to 13, for example. I just wrote down the list. Suppose every integer n, every integer k, such that k is at least 2, but strictly less than n, is a product of primes. I must show n is a product of primes. How is that? There are two cases. In the first case, n is prime. And we're done. N is a product of 1 prime. In the case 2, n is not prime. So then n factors k1 times k2, where k1 and k2 are both between n and minus 1. Right? If a number is not a prime, it factors into 2 factors, both of which are bigger than 1. But by the induction hypothesis, k1 is some product of primes, and k2 is also a product of primes. So when I multiply k1, k2 with these exponents, could be 0 or positive. It's p1 to the e1 up to p r to the e sub r times p1 to the f1 up to pr to the f sub r. That's p1 to the e1 plus f1, e2 to the e2 plus f2, pr to the er plus fr. Product of primes, so we're done. So this is a very simple proof by induction that every integer is a product of prime numbers. I still have to prove uniqueness, but I think maybe all of this is enough for one day, and I'll prove uniqueness first thing tomorrow morning. Okay. Any questions so far? We cover a lot, but again, as I keep reminding everyone, one day of class is a week's work during the semester. So every class we do have to cover a lot. Okay. All right. That's it for today. Be well all. I'll be back at 11 o'clock tomorrow.